My name is Varun Yarabarla, and this is my video lab report on constant velocity. The point of this lab was to find a real-life example of something moving at constant velocity and understand just how it works through the application of Newton's second law of motion. In order to show this, a Lexus RX 350 was recorded moving at constant velocity, and its motion was analyzed using tracker and then modeled through VIDLE. The computational model and experimental model were then compared to understand that there was no net force acting on the system and that there was constant velocity. There are two principles that can be applicable to this lab, Newton's first and second laws of motion. Newton's first law states that an object in motion will keep moving uniformly unless acted upon by another force. In other words, if it's moving at constant velocity, it'll keep having that constant velocity unless affected by a net force. Taking that further, we have Newton's second law, which is F equals ma. Deriving that further, we get the final equation here, velocity final equals velocity initial plus F net divided by the mass times delta t. We know that this third portion of the equation, if equal to 0, will mean that the velocity final is equal to velocity initial, which means constant velocity. Thus, we know that the mass and delta t are already not equal to 0, so the net force acting on the system has to be 0. So this is the video and tracker. The car is the system and everything else is the surroundings. I plotted the points, and the graph on the upper right-hand corner turns out to be linear, which shows that there's constant velocity. Only the x-axis matters in our case, and the y and z are irrelevant. I chose the positive direction to be towards the right. The data table on the bottom right is very useful to us as well, because it gives us the time and the position. The time goes from 0 to 2.135 seconds, and the position goes from 0 to 7.159 meters. We take this data and plug it into the skeletal code that was provided, along with some other information, such as the car's mass, which is shown here. The initial position of the car was 0, and the initial velocity is something that we have to calculate through the equation change in position over change in time, as it was done here. And we get a value of 2.909 meters per second, which was then put back into the skeletal code here. This value of 0.01 is the change in time, and that is done with such a small number so that we can have multiple points and have more accurate results. This while loop here keeps iterating until the final time of the video, which is 2.135 seconds. The F-net equation here shows that there's 0 net forces acting upon the system. This equation here, or assignment statement, is essentially Newton's second law of motion, which we said earlier. In this case, this part of the equation would become 0, and then the initial velocity would then equal the final velocity. Then, that is taken and reused here in this line of the code. This is the position equation relating the velocity and the progression of time, which shows the shift in the car's actual position. When this code is run, we see this. We get a computational model which is representative of the movement of the actual car. If looking at the graph of the predicted motion and the observed motion, they are the same, as can be seen here, except for the fact that the predicted assumes constant velocity and doesn't go as far as the observed, which shows for this discrepancy in changes. But for the most part, the slopes are both positive and both lines are linear, which shows that they have constant velocity and they are very close in what they're showing. Let's answer the questions related to the lab. The first one, what if? If the axis was changed, the car would be moving along the negative x direction rather than in the positive like it is now. The slope of the graph would also change. Rather than being up and to the right and positive, it'd be negative and could be going down and to the right. What does it mean? The second question. There's not a certain way to tell how many pushes or pulls, aka forces, there are that are added together. This is because they can't be measured right now. The only thing that we know is that there's a constant velocity, which means that the net force has to be 0 according to Newton's second law of motion.